Thank you so much, Reno, for being here today and giving a nice overview of the topic to start us off. Our next speaker, Garrett Schreiner, is Freeway Operations Engineer at Minnesota DOT, and he will be providing an overview of his agency's use of Q warning messages. Hand it over to you, Garrett.
Thank you, Alex. As Alex said, I'm Garrett Schreiner, Freeway Operations Engineer at MnDOT, and we've been working with Q warning systems for some time, and happy to provide some of our experiences and lessons learned. Next slide. So MnDOT has used three, I'll say, dedicated or permanent locations. Um, in the past. We currently, only one of those three is still in use. We started our first kind of step into it wasn't a dedicated Q warning system, but it was integrated into our intelligent lane control system that we had on 35W and 94 in the Twin Cities metro area, where we had lane control signals every half mile through for a significant stretch of both of those corridors. We put in um, variable speed limits, but they weren't actual speed limits based on Minnesota statute. They were advisory only speeds, and we kind of used that to help warn people of slowdowns ahead. There was some latency in the system. Our ATMS did some additional smoothing of the speed data that made it not as effective. The system currently is not in place, not because of that aspect of it, but more the hardware issue. We had significant maintenance costs with those devices. We opted to take those down and replace them with um, CMS every mile or so. The second one was it was mentioned in an earlier slide. Our university, the University of Minnesota, did a research project with us to set up a Q warning system in Minneapolis on 94, where we were looking at downstream conditions and warning traffic on a single DMS upstream. And it showed significant um, improvements and reduction in crashes, but there was kind of a footnote on that slide that it was looking at a very specific type of crash in one specific location. So the numbers may be somewhat inflated based on that. And also it was in the middle of a major reconstruction of an interchange in Minneapolis that reconfigured the layout of of where the ramps were coming in and where the exits were. So that alone had some impacts on could also have impacted the results there. That system, it was effective, but the algorithm used was um, a little complicated, and and we were looking at other options. Instead of incorporating that algorithm into our ATMS, we were looking at maybe some simpler but just as effective options. Um, and and that's kind of what we landed with. The third system, which is currently still in place, is we have a bridge that heads into St. Paul on US 52 that has a kind of a significant vertical curve, and it ends in a interchange with 94. Um, in that location, the center lane always backs up, and we have significant speed differentials between the center lane and the left and right lanes. And the lane assignments at the interchange are a little unintuitive. You have to be in the left lane if you want to go to the right, which would be eastbound 94. Um, so we get a stopped center lane, and then people in the free flow left lane that are stopping and trying to get into that center lane once they realize they selected the wrong lane. So we incorporated a Q warning system into our DMS that's upstream. And in addition to a stop traffic ahead or a slow traffic ahead message, we also put what's shown on the screen here. We emulate a static sign with the lane assignments to give people a little extra when there's stop traffic in that center lane, give people a little extra warning so they can pick the correct lane before they get to the interchange. That has seemed to be very effective. I don't have specific crash numbers on any reductions, but subjectively it has been very effective, and we can watch from the operation center that being deployed as traffic slows down in that center lane. Next slide. So our current practice in Minnesota is we really are using the queue warning systems as part of our work zone management, congestion management for work zones in our intelligent work zones or connected work zones. Our typical setup is we'll have 3 PCMS or 4, depending on the location and the geometry, that are spaced about a mile apart, trying to incorporate upstream of the expected end of queue. And then we will have temporary detection at half-mile spacing if we aren't able to utilize our existing mainline detection. And the way we have it set up in our system, we basically have 4 different messages that are always active, but with varying levels of priority. The um, the highest priority would be the stop traffic ahead. And so if we're detecting traffic speeds 30 miles an hour or less within 2 miles, we'll display the stop traffic ahead, be prepared to stop message on the PCMS. The next lower priority would be slow traffic ahead. So if there's no stop traffic ahead trigger, then it'll revert to the slow traffic ahead, use caution. If it's detecting 45-mile-an-hour speeds within 3 miles, and if it is not detecting that, it'll be blank, or we'll have a travel time or a delay time posted on the PCMS. We also will blank the sign if traffic is detected to be stopped at the PCMS. We don't need to tell them that there's stop traffic ahead if they're already stopped in traffic. So we'll either just blank the sign or change it to a delay message so people can expect how long they're going to be stuck in that queue. Next slide. We also incorporate an active zipper merge into our system in certain locations at the request of the project engineer or a project manager for a specific work zone. And the way that is set up is we look at the through lane, the lane that is not ending. And if occupancy of that lane is greater than or equal to 25% based on our traffic detection, we will turn on the merge ahead, use both lanes message on the PCMS. One thing that we do when we set up these systems is we will monitor them periodically to make sure that they're working as intended. And if they're not, we can tweak those speed thresholds. There are variables within our ATMS that we can set, and so we can get that working properly in the correct location and turning on when they're needed, but not activating when they're not needed. We can verify them on camera if we have a camera view, or have someone in the field verify that they're working properly. Otherwise, they do run autonomously, and we kind of set it and forget it unless we hear after we've tweaked everything and made sure it's working properly. And unless we get a complaint from someone in the field or one of our operators notices anything, they just kind of run on their own. And in our ATMS, we can see what's being displayed on those PCMSs or our permanent DMS, but they are shown as a automated message, so they don't clutter up our operators' screens with all of their user deployed messages for incidents. Next slide. So some lessons learned after operating these systems. We have looked at using probe data for our detection method, and probe data is great. And if we have an existing queue that's kind of static, I would say, probe data is great. One area where we found an issue is when a queue is first forming, or if a shock wave is traveling upstream, the timeliness of the probe data, at least the probe data that we have integrated into our system, is it's not quite timely enough for a queue warning message. Um, so we typically will use the probe data if we're going to post a delay message or a travel time, but to actually activate the stopped or slow traffic ahead message, we use either our permanent or temporary detection. One thing with that's, I don't know if this is unique to Minnesota, but the way our system is set up, we have our our traffic detection is set up where it will automatically fail a detector if we get a high occupancy spike, and then which would normally indicate that there's a problem with the detector, and then our system will stop using that detector in its calculations and algorithms until the occupancy values have come back to what it expects as a reasonable level. This works great, except for places where there actually is stop traffic, either due to an incident or a work zone. It'll make our detectors auto fail when they really shouldn't. So we had to modify our ATMS to allow us to kind of ignore the auto fail condition, specifically in queue warning, in the queue warning messaging. That was something that we found out after the fact as we were working with these systems and noticing that we were having some issues with the detection failing, or the ATMS thinking the detection was failed. Another thing when we are planning for these um, queue warning systems approaching our work zones, it is important to have somewhat of an idea of where the end of queue is going to be, just for determining where to place the PCMS and the temporary detection. Um, but if we get it wrong, this we're mostly using trailer mounted systems, so it's not a huge deal to go out and adjust the layout. But it does definitely helps with setup if we have a good understanding of where we expect those queues to be. Next slide. Another lesson learned. Um, our system is set up to be able to display the location of the stop traffic. You know, it'll look 2 or 3 miles downstream, and when it returns the the information back to the system, it will give us the location, whether it's a mile ahead, half a mile ahead, 2 miles ahead. And we used to put those on the messages, stop traffic 1 mile ahead. Um, but we've moved away from that to try and simplify our how we have it set up in our system, and we no longer display the actual location of the queue. We just say stop traffic ahead, be prepared to stop, or something a little bit more generic. We want the drivers to be paying attention. And it also helps if there's a fast moving end of queue or shockwave, that it eliminates any worry about latency in the system. You know, if we say it's a half mile ahead, but they encounter it, you know, sooner than that, we don't want to. Um, we want people to just be aware that it is ahead, not necessarily saying the exact location. Um, Another lesson learned, this is more on the contracting side of the system. We used to incorporate the intelligent work zones uh, project by project, including it um, in each construction project, but that was a challenge trying to integrate the systems with several different vendors, traffic control subcontractors. So we decided several years ago to pull that out and run it as kind of one master contract from our traffic management center. We are that way we're dealing with one vendor. We've integrated the system already. It's very easy to set up and move. We have pay items for relocating systems. Um, and then it also, that is their only focus for that contract. We don't need to worry about making sure that it's, you know, a priority for the prime contractor. It has just made things work a lot more smoothly. The only issues, we need to make sure we don't interfere with the work of the prime contractor on those construction projects. It also gives us really good responsiveness if there's technical or hardware issues that we've found. Next slide. All right, so this just kind of in general, the map here just shows all of the detector stations that we have in the Twin Cities metro area. We have very good coverage, which allows us to set these systems up on the fly, wherever they're needed. Um, it gives us a lot of flexibility. Um, the only the only issue is putting in temporary detection if where it is needed is due to a construction project that's impacting our um, traffic detection, um, which usually our Q warning systems are outside of the work zone, approaching the work zone. So we are able to utilize our permanent detection quite a bit. But with uh, our extensive network of traffic detection is pretty flexible. We can put these systems pretty much wherever we need to. And then having it part of our ATMS and incorporating the PCMS into our ATMS, uh, we're able to use our permanent detection, our permanent message boards as well to supplement the PCMS, especially in areas where maybe there's not a lot of spaces on the shoulder to put a trailer mounted message board. We can utilize our existing overhead permanent message boards. All right, and that is all I have. Thank you.